Friends, let us now go into the next property that we are going to study here in terms of the trends in the periodic table. Now, the first property that we had studied was the atomic radius. Next was the ionic radius. Next, we had studied the ionization enthalpy. Next, we had studied the electron affinity, which is also called as electron gain enthalpy. So after that, we are now going to do the fifth property, which will be electronegativity. Let us look at the meaning of electronegativity. Like say for example, we have got two atoms which form a covalent bond. Like say for example, in the case of HCl. Now here we have hydrogen atom and we have got chlorine atom. Now we know that chlorine, it basically has an electronic configuration of 287, due to which it is desperate for electrons. Hydrogen can even lose its electron. So what happens here is that they form a covalent bond wherein this cross is the electron of hydrogen and this dot is the electron of chlorine. And hence we can have this sharing of this pair of electrons. So whenever we have such a sharing of this pair of electrons, this is a covalent bond which is formed. Now in this covalent bond, there are some strings attached. That is, what happens here is that chlorine being more electronegative means basically it is more desperate for electrons. Why? Because it has an electronic configuration of 287, due to which it requires one electron more to complete the electronic configuration of its nearest noble gas to become stable. Chlorine requires one electron more. And because it requires one electron more, therefore it is more desperate for electrons. Therefore, what it tries to do is that it tries to attract this shared pair of electrons or shift this shared pair of electrons slightly towards chlorine in this covalent bond. So what happens basically is that this shared pair of electrons, which should be exactly in between hydrogen and chlorine, it is not so. What happens is that this shared pair of electrons, they move slightly towards chlorine, due to which there is a partial negative charge which is developed on chlorine. Now, when we say a partial negative charge, it is because electrons are negatively charged, right? So because electrons are negatively charged, whenever there is a shifting of the shared pair of negatively charged electrons towards chlorine atom, therefore chlorine gets a negative charge which is not -1. That is one thing which you need to understand and avoid making that mistake. So this is not a -1 charge which is getting. If chlorine would have had a -1 charge, when both these electrons would have completely come to chlorine, in that case it would have been a 100% pure ionic bond, wherein both these shared pair of electrons, both these electrons here between hydrogen and chlorine, if they would have totally come to chlorine, in that case chlorine would have got -1 charge. However, in this specific case, as you can see, chlorine will not have a -1 charge. It will have a charge which is minus delta, which delta shows a fraction of a charge. It shows it can be either 1/4, it can be 1/8, it can be 1/16. It can be any fraction of a charge. It will not be a whole number. It will not be 1. It will be any day lesser than 1. Now, how much lesser than 1 depends upon the difference in the desperateness for electron between these two combining atoms. In the case of hydrogen, it has a tendency of giving away its electron. And normally that is the reason why you can see a lot of situations wherein hydrogen forms a proton. What I mean to say is that a hydrogen forms a H plus ion because it has a tendency of giving away its electron to a suitable electron acceptor. And that is the reason why here because the shared pair of negatively charged electrons, they move slightly towards chlorine, they shift slightly towards chlorine, hence the hydrogen here will get a slight positive charge which is plus delta. And this is this phenomenon due to which chlorine is attracting the shared pair of electrons toward itself in a bond. This phenomenon is called, or this property is called as electronegativity. So what is electronegativity? Electronegativity is that property due to which one atom, it attracts the shared pair of electrons involved in a covalent bond towards itself. That property is called as electronegativity. So now once we understand the meaning of electronegativity, let us now try to understand a very important concept about electronegativity. That is, electronegativity is not a measurable property. Unlike in the case of ionization energy, we were able to measure the value of ionization energy. We were able to measure the numerical value of electron affinity. However, in the case of electronegativity, we can't give a perfect value for electronegativity. The value of electronegativity has to be judged. It has to be found out. So basically, there were different scientists named Mulliken or Alfred or Pauling. These scientists tried to give their own scale for electronegativity. The very big problem with electronegativity finding of any element was that electronegativity of one single element, it keeps on changing depending upon the element with which it is attached. However, Pauling's scale, one of the three scientists whom I had named, whose name is Pauling, his scale is considered most widely as of now as the scale for electronegativity. What Pauling has done is that he considered the electronegativity of fluorine atom, he had considered its value as equal to 4. He had taken it as equal to 4 because fluorine is the most electronegative element in the entire periodic table, my dear friends. This is one thing which you need to remember. The second highest electronegativity is that of oxygen, having electronegativity 3.5. So in the case of fluorine, because it has an electronegativity of 4, means the highest electronegativity in the periodic table, he had arbitrarily given it a value of 4. And after he has given it the value of 4, he gave the electronegativity of the other elements in the periodic table as a comparison, in comparison to that of fluorine. So therefore, the other electronegativities of the periodic table can also be given with respect to fluorine. So the trends in electronegativity is something that we are going to study right now. Now, basically as I have already told you, in the case of the electronegativities of element, they are not fixed for one single element also. Like in the case of fluorine, the electronegativity might be 4 when it is combined with one element. It might be 5 if in case it is combined with some other element. It might be 1 if in case it is combined with some other element. So the value of electronegativity of an element, it keeps on changing. So that is a very interesting concept that you guys need to understand. This concept will be important for you when you study organic chemistry, when you will be asked, a little bit of difficult questions related to the bonding. That is, you will be needed to find out which of the given bonds will be weaker and they will be broken. So, like say for example, you will be asked whether trichloroacetic acid will be a stronger acid or acetic acid will be a stronger acid. So that concept you need to explain, you need to understand, and you need to answer such questions if in case you have understood the concept of electronegativity very well, because there is the actual application of electronegativity. What I will do right now is that I will try to give you one of the examples so that you can actually get an idea, a nice idea about what I am talking about. Let us consider a situation wherein we have a centrally placed carbon atom. Now, when we have this centrally placed carbon atom, we have two different scenarios. First scenario, wherein this carbon atom is bonded to 3 atoms here. Okay. Now, this is, say for example, here this carbon gets connected with another carbon atom here. Okay, or with another atom here. Right now we are talking about the electronegativity of carbon atom, how it changes depending upon which element it is bonded to. Next, let us consider the same carbon atom when it is bonded to 3 hydrogen atoms. So here we have 1 hydrogen atom, here we have 2nd hydrogen atom, here we have got 3rd hydrogen atom. So here we have 2 different scenarios wherein this same carbon atom here is connected with 3 hydrogen atoms, here connected with 3 fluorine atoms. Now this fluorine element and this hydrogen element are contrast in terms of electronegativities, because hydrogen's electronegativity is 2.05, which is close to 2, and fluorine's electronegativity, as we have already considered according to Pauling scale, is equal to 4. So there is a huge difference in electronegativity between hydrogen and fluorine. So therefore this is an extreme situation scenario example wherein you will be able to understand the difference. So let us see what happens here. What happens here is that fluorine, being more electronegative, it tries to pull the shared pair of electrons which is present in this covalent bond which is formed between carbon and fluorine, it tries to pull it towards itself. Hence, this shared pair of electron, it moves slightly towards fluorine. As you can see here, the electronegativity of fluorine is equal to 4, right? And because the electronegativity of fluorine is equal to 4, it will, like in the case of chlorine, it will try to pull that shared pair of electrons toward itself. So it does it here, due to which it gets a partial negative charge. Similarly, this fluorine gets a partial negative charge. Similarly, this fluorine atom also gets a partial negative charge. So what happens here is that carbon here, as you can see, its electron density, the electron density which is near to carbon, which was involved in the formation of the covalent bond, the electrons which should have been ideally exactly between fluorine and carbon now shifts towards fluorine, due to which all the electrons now have moved slightly further away from carbon, due to which now carbon will be now short of electrons, because the electron density has moved away from carbon. Hence, carbon will be now more desperate for electrons. Because it will be now more desperate for accepting electrons, for attracting electrons. It will now try to pull the shared pair of electrons which it has now in the bond with the other carbon atom with which it is present. Hence, now this carbon atom has now increased its electronegativity, because now it is more desperate for electrons, right, as compared to earlier situation. So because carbon right now is has more tendency to accept electrons or to attract the electrons with its neighboring atom, hence this carbon atom, it tries to attract electrons to compensate for the loss of electron density near it, so that the electron density from this nearby atom, if it comes near to carbon, it will lead to more stability for this carbon atom. Exactly the opposite happens in its bonding with hydrogen atom. What happens here, my dear friends, is that hydrogen, we know, has electronegativity of approximately 2, carbon has an electronegativity of 2.5, due to which, as carbon has greater amount of electronegativity value, carbon will in this case try to pull this shared pair of electrons towards itself. When carbon pulls the shared pair of electrons towards itself, carbon will have a value, electronegativity value. Here in this case it was plus 3 delta. Here carbon will have an electronegativity value of minus 3 delta, wherein each hydrogen atom will have an electronegativity of plus delta. In this situation, as you can see, carbon has more electron density towards itself. Because of the shared pair of electrons between carbon and hydrogen covalent bond, it has slightly shifted towards carbon, and due to which, my dear friends, as you can see here, carbon has a more amount of electron density towards itself rather than a situation wherein it would have been bonded with, say, other carbon atoms. It would have been a carbon-carbon bond chain network. In that case, in this specific situation, what happens is that carbon, because it has more amount of electron density which is present near it, it will try to release electrons which it already has towards the other carbon atom with which it has bonded here. So here we have another carbon atom. Now here we have a carbon-carbon bond, and in that carbon-carbon bond, now this carbon atom, because it already has a more amount of electron density near it than which is average or which is natural for it, therefore it will try to release some amount of electrons towards this carbon atom. Hence the electronegativity of carbon atom in this scenario will be decreased to some extent. So therefore, this carbon atom's electron density, electronegativity here, it decreases. Here the electronegativity of carbon atom increases. So the electronegativity of the same element can change depending upon which other elements atoms it is bonded to. So this was exactly the point that I was trying to explain to you. Now, as you can surely understand, the electronegativity concept is exactly the same as the concept of non-metallicity, and it is exactly the opposite to the concept of metallic behavior. So therefore, we can write down in short that the electronegativity, as we can say, is inversely proportional to metallic character, and in a similar way, we can say that electronegativity is directly proportional to the non-metallic character. So this is the conclusion that we can draw, because we know, my dear friends, what happens in the case of metallic character and non-metallic character, right? Like we have non-metals like chlorine and fluorine, which have greater amount of electronegativity, and hence more the non-metallic character, more will be the value of electronegativity. More will be the metallic character, like in the case of sodium, the electronegativity is very, very less, because it has very less tendency of accepting electrons or trying to pull electrons toward itself in a bond. Hence, the value, when the metallic character is more, the electronegativity is less. The tendency of accepting electrons, trying to pull electrons toward itself is less. In the case of metallic character, the opposite happens. The tendency of giving away electrons and forming positively charged ions is much more here, and which is exactly the opposite behavior of electronegativity. So this is the kind of conclusion that we can draw, wherein we compare electronegativity with metallic character as well as when we compare it with non-metallic character. Right now, let us understand about what happens to electronegativity values when we move from left to right in a particular period, as well as we move from top to bottom in a particular group. Let us look at what happens. First, let us see a situation wherein we move from left to right in a period. My dear friends, as we move from left to right in a period, we know that the metallic character, as we have already studied, the metallic character, it decreases, and the non-metallic character, it increases. Like say for example, as we go from sodium to chlorine in the periodic table, we know that sodium has a very less tendency, the least tendency in this particular shell. Sodium has the least tendency of trying to accept electrons. The tendency of trying to accept electrons, it keeps on increasing from sodium to magnesium to aluminum to silicon to phosphorus to sulfur to chlorine. We obviously are not including argon here, because we know that it is a noble gas, right? It has nothing to do with accepting or giving electrons, so it is totally out of the picture. So here, therefore, we are not discussing noble gases. So hence, we are talking about from sodium to chlorine, what is going to happen. As I have already told you, as we already know, as we have already discussed many times before, from sodium to chlorine, we know that the tendency of trying to accept electrons, try to put electrons towards itself, desperateness for electrons, from sodium to chlorine, it increases. So as we can, therefore, we can conclude here that as we move from left to right in the periodic table, the electronegativity values, it will increase, as happens from sodium to chlorine. Now, we know the reasons for that. The reasons for that will be exactly the 4 reasons which we discuss and which we require in each and every specific example that we have done out of these 5 examples, out of these 5 different properties. We know that first of all, it depends upon the number of shells, right? We have seen that, right? It basically depends upon first the number of shells. Secondly, it will depend upon the effective nuclear charge. Third, it will depend upon the electronic repulsion. Which is present. And fourth, it will depend upon something which is called as screening effect. So we use all these same 4 principles, the 4 different factors for determining the electronegativity also. So as we go from left to right in the periodic table, we know that the number of shells, they remain the same, right? So this factor, this is no longer a factor, a differentiating factor to differentiate between the electronegativities of sodium and chlorine. Next, we talk about nuclear charge. As we move from sodium to chlorine, we know that the nuclear charge, it keeps on increasing. And when the nuclear charge will keep on increasing, there will be a greater tendency by the nucleus to accept a negatively charged electron. Because more the nuclear charge, more will be the positive charge inside the nucleus, more will be the strength with which the nucleus will pull a negatively charged electron towards itself. So as the nuclear charge increases, we know that the value of electronegativity, it also increases. Here, so as we go from left to right, the nuclear charge increases, and hence the because electrons are added in the same valence shell, right? In the same third shell, electrons are added from sodium 281 to chlorine in the case of 287. Because 1 to 7 electrons are added in the same shell, therefore the number of shells is not a parameter here. Also here, in this case, the nuclear charge, as it increases, it will be the matter, it will be the property which can decide electronegativity. Next will be the electronic repulsion. As we know that as we move from sodium to chlorine, the electronic repulsion keeps on increasing, and that will be one of the factors which goes against the electronegativity. So because of electronic repulsion, as we move from left to right, the electronic repulsion increases due to which the disparateness with which electron is pulled is less. Hence, because it will be more unstable if the last electron comes. We know that in the case of electronic repulsion, there we have a situation wherein the noble gas, like argon, it has huge amount of electronic repulsion inside it, due to which means the electrons, they start spreading and the atomic size, it increases hugely in the case of noble gases. So next factor will be the screening effect. In this case, the screening effect will not be applicable because the number of shell is the same, right? Because the electrons are being added in the same valence shell. So the net factor here will be that the electron negativity, it increases because of the increase in nuclear charge. It should decrease because of the electronic repulsion. The next factor, the net factor here will be that there will be a net increase in the electronegativity because nuclear charge factor is much more profound. Its effect is much more profound as compared to the electronic repulsion. Now that we understand that, let us now look at what happens as we move from the top to bottom in the periodic table. That is, as we move from up to down in the periodic table. As we move from top to bottom in the periodic table in a particular group, let us see what happens to the electronegativity values. We know that as we move from top to bottom in the periodic table, the number of shells keep on increasing. So if the number of shells keep on increasing, the distance between the last shell and the nucleus, it keeps on increasing. As the distance it keeps on increasing, the nucleus, the positively charged nucleus, will have very less effect on its outermost shell electrons, and it will have very less capacity to attract electrons from the other atom toward itself. Hence, the effect of the increase in number of shells is that the value of electronegativity, it decreases. Next will be in terms of nuclear charge. Because the nuclear charge increases, the effect should be that the value of electronegativity should also increase. Next, the effect of electronic repulsion. Here, in a particular group, we know the number of electrons, the number of valence electrons is the same, right? If in case we look at halogens, in all the cases, in all the halogens belonging to the same group, all of them have 7 valence electrons. In the case of all alkali metals, all of them have same valence number of valence electrons, which is equal to 1. And hence, in the case of electronic repulsion, there will be no effect of this factor. So here I am writing down equal to. The one thing, my dear friends, that you need to realize, that as we move, as if in case we have 7 electrons in the case of, say, chlorine, and we also have 7 electrons in the valence shell of fluorine. Because the size of the shell of chlorine is greater, hence the repulsion between the electrons will be lesser in the case of chlorine, and the repulsion which will be observed in the case of fluorine will be much greater as compared to the repulsion, inter-electronic repulsion in the case of chlorine. Because in the case of fluorine, we have a situation wherein the electrons are very closely packed to each other. Hence, there will be repulsion, and hence the atomic size should increase in the case of fluorine, if in case it further accepts 1 electron. So therefore, let us now go to the last point, wherein we will be talking about the screening effect. Here, yes, there will be the screening effect which will be observed if in case we move from top to bottom in the periodic table, where the number of shells keeps on increasing. So when the screening effect keeps on increasing, the effect on the electronegativity is that the electronegativity keeps on decreasing, because screening effect, it further weakens the bond, further weakens the electrostatic force of attraction which is present between the outermost shell electron, that is valence electron, and the positively charged nucleus. And because it further decreases the electrostatic force of attraction, hence the nucleus is further weakened in its attempt to attract a negatively charged electron towards itself inside the atom. So let us write down the net effect which will be observed in this specific case. The net effect which will be observed will be that because the increase in the number of shells, the value of electronegativity decreases. This is the most important factor which affects around 70% of the entire decision making process. So here, because of the increase in number of shells, electronegativity should decrease. Here, according to, because of the increase in nuclear charge, the electronegativity should increase. Here, because of the screening effect, the electronegativity should decrease. So the net effect here is that the electronegativity will decrease as we move from top to bottom in the periodic table. So when we say top to bottom, let us consider a situation wherein we are going from top to bottom in the case of alkali metals, wherein we will be talking about the change in electronegativity as we move from lithium to, say, francium or cesium, whichever is okay with you. So here the net effect, let's write it down, the net effect. So here the net effect will be that electronegativity value, it will decrease as you move from top to bottom in the periodic table. Just so that there is no confusion, let us write down the electronegativity values of some of the elements, and which will help us understand whether the concept that we have seen up till now, whether it matches the reality. So let us look at the electronegativity values of some of the elements in the periodic table across a particular period, as well as moving from top to bottom in a particular group. So if in case we go from, if in case we consider the first scenario, wherein we have, atoms like, starting from, say, sodium. So let us consider the electronegativity of elements starting from sodium to chlorine. So if in case we write down the elements first, so this is sodium, this is then magnesium, this is aluminum, this is silicon, this is phosphorus, this is sulfur, this is chlorine, right? We know that argon will have no tendency of trying to accept electrons or try to pull electrons in any bond, because it hardly forms any bonds. So therefore, let us write down the electronegativity values which will be applicable here. In the case of sodium, the electronegativity value is equal to 0.9. In the case of magnesium, it will be 1.2. In the case of aluminum, it will be 1.5. In the case of silicon, it will be 1.8. In the case of phosphorus, it will be 2.1. In the case of sulfur, it will be 2.5. And finally, in the case of chlorine, it will be 3.0. So as we move, as I have just shown you here, as we move from left to right in the periodic table without exception, that is a good thing about studying electronegativity, right? Because in all the other situations, we had exceptions. So we had to break our head behind all those exceptions. In electron affinity, in terms of in ionization energy, in terms of atomic size. So there were always exceptions, which was actually unnecessary headache. So here we don't have the unnecessary headache. So we have a particular pattern. As a matter of fact, this pattern is very astounding. The values that I have written here, as I have told you, is according to Pauling scale, because all the values that you will ever see in any book will be according to Pauling scale without even requiring any mention of it. So here in the case of sodium, as you can see, the value, it increases by 3. This is simply the table of 3 that you can see. We know that 3 3s are 9, right? So 3 4s are 12, 3 5s are 15, 3 6s are 18, 3 7s are 21. So up till here, it is just a table of 3. So it's very easy to remember the values. In the case of sulfur, instead of 2.4, it is 2.5. And finally here, we have 3.0. So this was what happens as we move from left to right in the periodic table. Let us now look at a situation wherein we move from top to bottom in the periodic table. So let us consider a group wherein we move from top to bottom in the periodic table, and let us consider the electronegativity values and see if the electronegativity values confirm our theory. So here let us consider the halogen group. That will be better, right? Group 17 elements. So let us consider group 17 elements, wherein we start with fluorine, the most electronegative element of the periodic table. Then after that chlorine, and then we will have to go to bromine. Then we'll go to iodine, and then we'll be going to astatine, which is represented as AT, because AS is arsenic. So once we go into this, let us quickly give their electronegativity values. So in the case of fluorine, the electronegativity value will be equal to 4.0. Now you guys know this very well, right? In the case of chlorine, the electronegativity value will be 3.0. In the case of bromine, it will be 2.8. In the case of iodine, it will be 2.5. In the case of astatine, it will be 2.2. So as we see, as we have already concluded, as we move from top to bottom in the periodic table, the electronegativity value, it should keep on decreasing. So as you move from top to bottom in the periodic table, starting from fluorine in the halogen group, starting from fluorine to astatine. As you can see, the electronegativity value, it keeps on decreasing from 4 to 2.2. Again, the good thing here is that there is no exception. So it is always better to understand such type of theories, right? So here, as you can see, the electronegativity value keeps on decreasing as you move from top to bottom in the periodic table, which exactly matches what we had predicted. So I hope so, my dear friends, that you have understood the extremely important topic of electronegativity.